All right, let's continue. So in the so the goal of today is to describe light propagation through bulk tissue, so through larger pieces of tissue. And before the break, we saw that that if there is some kind of organization in the tissue, so for example, a little bit cartoonish in the left-hand side, where there are big scatterers that are contained in cells. So that means that there will be a distribution of distances between them. They will not be completely randomly distributed. Then we do have to take that into account. The process is then called dependent scattering. Depends on the organization of the scatterers. But we also saw that we can still use our familiar optical properties. We can still define a scattering coefficient. We can still define a phase function. We can still define scattering anisotropy. So we can keep using those. The only difference is that we have to be a little bit careful when we calculate them. We have to take them into account the organization. We have to take into account the volume fraction. All right. Then to describe this light propagation in bulk tissue, we do use a little bit of a different set of properties, radiometric quantities. So how to describe the transport of photon energy? Well, the first one is a very familiar one. That's the intensity. In the light transport literature, it is also called irradiance, but I'll try to stick to intensity. Its units, as we saw before, were watts per square meter, or if you like, you can write that as joules per second per square meter. Basically, the photon energy per unit area per unit time that is incident on a tissue surface, because this intensity is usually used, reserved for something that is either incident or escapes from a surface. We can use it to just to quantify tissue illumination. Because it is about if it's about illumination, that means that it depends only on the geometry. It does not depend on the optical properties of the tissue yet. It only describes how much light is incident. Second one is the radiance, which is a local property inside the tissue. We can define an area in the tissue. And then the radiance is defined so that it's an area in the tissue at the location R. It's three-dimensional, so it's a vector inside the tissue. And then the radiance is the optical power in watts flowing through a unit area located at R into a unit solid angle in star radians into a given and that unit solid angle is centered around the direction vector S. So we have a location in the tissue that's given by a vector R. We have let's say an observation direction where we evaluate how much power is flowing in the direction S through an area over a small element of solid angle. So power through an area is still watts per square meter, but since we're also evaluating in a small cone, it adds the unit per star radian. So the radiance has unit watts per square meter per star radian. Then if we integrate, so we're still inside this test area inside the tissue. If we now integrate all the power over over the whole solid angle, so over 4 pi solid angle, we get another quantity called the fluence rate. Because we performed an integration over star radian, that drops out. So the units of fluence rate are again familiarly watts per square meter. So the fluence rate at a location R in the tissue is the optical power that flows from or to this unit area. Through that unit area is probably best to say in any direction. We've integrated over integrated over the direction S over all these unit solid angles, so that drops out. Formally, that is then written as this integral, so the integral over solid angle omega over the complete solid angle, so omega is 4 pi. Fluence rate is a really important quantity because if we multiply the local fluence rate somewhere in the tissue with the local absorption cross section, sigma A, we're essentially calculating the locally absorbed power. So how much power in watts is absorbed at that location. And that can then be used, for example, for therapy, or we may want to calculate it to be sure that we don't reach a damage threshold, for example, or etc. So fluence rate is an extremely important quantity. And if we multiply the local fluence rate with the local absorption coefficient, so mu a times the fluence rate, then we get the local absorbed power density. I just realized that the symbol on the left-hand side is not updated. I will do that later. But this would give us the yeah, the absorbed power density. So the number of watts per cubic meter that is then absorbed in a piece of tissue. Same reasoning if you want to calculate, if we want to do damage or avoid damage, we need this number, and for that we need the fluence rate, local fluence rate. Other quantities that are convenient is to look at energy fluxes, directional energy fluxes, or power fluxes. We can define again an area dA and look at the power flowing through that area, but that integrate the escaping power or the transmitted power through that area over half solid angle. So if we want to to calculate the net power flowing in the let's define the positive direction as going from left to right here. If we want to calculate the net power flowing in the positive direction, watts per square meter, then we integrate the radians over angles over the whole azimuthal angle, so that's the factor 2 pi, and in the forward direction from 0 to 1/2 pi sine theta d theta. Same thing we can do for the power per unit area into the negative direction. That would be F minus the red term there. So that would give us yeah, basically the power in the other half sphere. So from that we can, if we're interested only along this line, we can define the net flux as the difference between the flux in the positive and the negative direction, and we can define the total flux as the sum of these two. That is then the total flux going through that unit area. So for an example, if we would again take this piece of tissue, illuminate it with an intensity E, and we would look at the surface or just below the surface, then we define the positive direction as along the direction of the incoming intensity. Then F plus would basically equal the incident intensity because nothing would have happened yet. And the flux in the negative direction, the minus direction, would equal basically the escaping power from this tissue. So everything that escapes in any direction from this tissue, also in watt per square meter. So the reflectance R. All right. So to describe now this transport of energy, we can set up the radiative transport equation. I have asked you to prepare for this class by looking at a movie that already introduces that. So I assume that you have that you did so. So I'm not going to go into too much details of this equation. It is basically an energy balance which tells us in differential form that the change in energy or the change in power is a sum of gain terms and loss terms. So we can have if we consider power traveling along a certain direction, then we can lose some of that power just by divergence of the beam. So the beam spreads out. We can lose power because it is either absorbed or scattered out of the direction of observation. That's extinction. That's also a loss term. But we can also gain some power. There can also be power, optical photons, power scattered into the direction of observation. So that would be a gain term. And finally, there could also be a light source, for example, a fluorescent molecule in the tissue. So that could also generate light. So we could also have gain terms there. So this balance between loss terms and gain terms will tell us the net change in power over time. So this is in differential form. We can write this in integral form as well. As you can see, that expression is slightly more complicated, but the terms are more or less the same. So on the left-hand side, we have the change in radians. So we can set it up as a balance of radians. We have the change in radians as a function of time on the left-hand side. On the right-hand side, we first have a loss term. That's the gradient of the radians. So there is a divergence of the radians. The second term is losses due to absorption and scattering. So there's mu t, the sum of absorption coefficient and scattering coefficient. And then there is gain terms. There is light scattered into the direction. So um, that scales with the scattering probability. So the scattering coefficient is in there. And then between the square brackets, there is an integral that basically says we are going to sum up light coming from any direction being scattered into the direction of observation. Again, the direction of observation is S in this case. And the most right-hand term is the possibility of a light source at location R. So if you have a stationary response, so time independent, so the light is always on, it's not a pulse laser or something, then this equation is going to be time independent, and then the left-hand side will be 0. So that simplifies it a little bit. But still, this is extremely difficult to solve because we have 6, or even if time is there, 7 independent variables in this equation. We have 3 for the positions, x, y, and z. And we have also 3, because it's a three-dimensional situation, 3 elements in the vector s for the direction that we're looking at. So sx, x, sy, and sz, and then maybe even t. So it's an integral differential equations with 6 or even 7 independent variables, and that is, you can only solve it in the most simple of configurations. So what I want to do is to illustrate trying to solve this in one dimension only. So that greatly reduces the number of parameters. And I think it's important just to show you how derivation like this is done, and also to because we can draw some conclusions in the end that also hold for the 3D case. So it is a little bit stiff on the math, so bear with me. I'm not going to ask you any questions about the math, but in the end we'll draw some conclusions, and these, of course, I would like you to take note of. Okay, so this is the geometry. We have a 1D cylinder with which is infinitely long, or has a certain length d. We'll specify that later on. But in the middle of it is a volume element dv. Volume length element dl should be better, but let's stick with this terminology. So there's an element dv in there. Because we're only looking in one dimension, this whole direction s is either along the axis of the cylinder or in the plus direction or the minus direction. So the direction s is simplified. Because it's 1D, there is no solid angle, so the terms with the omega we can simply ignore. There is not much spreading of the beam. The only thing is, the only things that we really need to take into account are absorption losses in dV and scattering losses in dV. We're going to ignore source terms, so that simplifies things a little bit. So the only gain term that we can have is some scattering from anywhere along that cylinder into the volume element dV. So let's first consider a cylinder with length d. The length of it says thickness here, but the length of the cylinder is a better term. An intensity or a radiance I enters from x is 0 in the plus x direction. So that is what you see on the left-hand side in the drawing. I in watts per square meter. Okay, I said 1D, but let's for argument's sake define a very small area so that we can get rid of the per meters later on. Then the end of the cylinder is at XSD, so the total length is D. And then we can define some properties in that volume element. We can define an absorption coefficient, mu a, and I've added the subscript 1 there to keep in mind that we're looking in one dimension only. We can have a scattering cross-section as a coefficient there, also per millimeter, and we can define a phase function. So normally the phase function would describe how light is scattered from one direction into another direction in 3D. But since we're working in 1D now, it basically means that light can only scatter into the direction, keeping the same direction that it was traveling, or it can reverse direction completely and go back into the direction where it came from. So the phase function in the 1D case gets a lot simpler. Other than that, the interpretations of these coefficients are exactly the same as in the 3D case. So mu a 1 times dx is still the probability that the photon is absorbed when it transverses this infinitesimally small distance dx. Mu s times dx is the same thing, the probability that the photon is scattered when it traverses that infinitesimal distance dx. And the phase function, if we multiply it with mu s1, then it is the probability of mu s1 dx1, then it is the probability that the photon is scattered from direction x to direction x prime when it is transversing an infinitely small distance dx. So the interpretations are just the same. So now we can take a little closer look at this 1D phase function, because we only have we basically only can have forward scattering that retains the direction, so purely forward scattering, or purely backward scattering where it reverses direction. So let's manipulate that phase function a little bit. Let's have plus refer to the plus x direction, and a minus refer to the minus x direction. Then for forward scattering, we can define a symbol PF, which would in the terminology as we had before would be plus plus, so coming from the plus direction, scattering into the plus direction, but forward scattering would also be equal to P minus minus, so coming from the minus direction, the minus x direction, and then scattering into the minus x direction, so retaining direction. And likewise, backscattering would mean that either mean initially traveling in the plus z direction, but then being scattered into the minus z direction, or initially a photon traveling in the minus z direction, but scattering into the plus z direction. So these are the two possibilities, or the four possibilities basically. But we also know that if a photon is incident in the plus direction, it either scatters in the plus direction or in the minus direction, in the plus direction or in the minus direction. So that means that the sum of P plus plus and P plus minus has to be 1, because any of these two happens, but one of them will happen. So the sum of these probabilities has to be 1. Same thing for P minus minus plus P minus plus. So if a photon is traveling in the minus z direction, then it either retains its direction or it reverses. Any of these two happen, and their total probability has to be 1. So we can use these definitions to define a so-called backscatter coefficient. So we take the scattering coefficient, the total strength of scattering, and multiply that with the probability of reversing direction. So we get a compound parameter, P plus or minus times the scattering cross-section, which has to be equal to P minus plus, which is also a reversal of direction, times the scattering coefficient, is equal to PB, the backscatter probability, times the scattering coefficient. So this is the backscattering coefficient. We can also calculate the scattering anisotropy for this 1D phase function. So that would be a G1D, simply by following the definition. So the anisotropy is defined as the average cosine, the expectation value of the cosine of the scattering angle. Well, in this case, we can have only scattering into the direction 0, that's forward scattering, or in the direction pi, which is backscattering. So the average cosine of the scattering angle is going to be the probability of forward scattering times the cosine of 0 forward scattering, times the probability of plus the probability of backscattering times cosine pi, which is the backscatter direction. So if we combine these, then then we can write this combined with the fact that that the sum has to be 1. We find that we can express this scattering anisotropy as 1 minus 2 times the probability of backscattering. In view of the time, I will leave it up to you to verify that this is correct. Or the other way around, we can express the backscatter probability as a function of this anisotropy value. All right, an updated list. The first 1, 2, 3 elements I already discussed. We now have the backscatter coefficient as an extra parameter. The probability, so backscatter coefficient PB times dx is then the probability that the photon is backscattered when it traverses an infinitely small distance dx. Okay, so with this we can now try to set up our power balance for the fluxes. So what we're going to do is in this small volume dV, which extends from x to x plus dx, we're going to look at fluxes in the forward direction and fluxes in the backward direction. So on the left of that volume, you see defined flux f f plus of x, that is at the location x. F minus of x, that is the flux in the minus x direction, also defined at that interface at x. And on the right hand side, you see defined f plus x plus dx. So that would be the flux in the positive x direction, but then defined on the other side of that volume. We're going to make the assumption here that we can add intensities and not the fields. That may seem a little bit contrary to what we discussed before the break, where we said we have to take into account these interferences. But the idea is that we do that beforehand. We calculate dependent scattering, so taking into account interferences between fields, in order to calculate the scattering properties, in order to calculate scattering coefficient or phase function. And once we have that, we've taken that into account, and then going forward, we can simply work with intensities. So that is where we're here now. Okay, so let's set up equations for this forward and backward fluxes. So the geometry stays the same. So we can now look at the change in flux in the positive direction as the light travels through that small volume. So that is basically the difference of the flux after the element and the flux before that. So that is the left-hand side of this equation. On the right-hand side, we set up the power balance, so losses and gains. The top row on the right-hand side shows losses. So mu a dx is the probability of absorption as the light travels through dx. So the minus sign is a loss. So minus fx mu a dx is the loss term here. There's also a loss term for scattering. So same thing. Mu s times dx is the probability of scattering in that volume. So if you multiply that with the flux, then we get the loss of flux as it travels. On the other hand, not all of it is lost. Some of the scattering is actually in the plus direction, so that so we can add that back as a gain term. That is the first term on the lower row of the right hand side. So f plus times p plus plus, and there can be a gain term from light that was traveling in the minus direction, but it is now scattered into the positive x direction. So that is the last term in these equations. So we have losses due to absorption and scattering in both directions, but we have and the gain terms are due to scattering in the plus x direction. So that can be either from the light that was already traveling in the plus direction, or from light that is traveling in the minus x direction, but that has now reversed course. Okay, so we have this difference. We can make dx really, really small and then divide by dx. So basically we make it into into a differential. So then the left-hand side becomes the dx dx of f plus. And there again, you see listed the loss terms now combined. So mu a and mu s are combined between the first square brackets. That's the loss terms, and then the gain terms are the last two terms. We can try to eliminate this phase function of this this phase function that is still in there. So p plus plus times mu s can be remanipulated because p plus 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 p plus minus had to be 1. We can manipulate that a little bit to replace p plus plus, and then and then multiply out with the scattering coefficient. So the first term 1 times the scattering coefficient just becomes the scattering coefficient, and the other term times the scattering coefficient we just defined a few slides ago as the backscatter coefficient. So we can replace this term, this product here, with mu s minus mu b. And of course, mu b is already present here in this part as well. So then we can regroup a little bit. First, on the right-hand side, first term expands the scattering and the absorption coefficient again. So the first term is lost due absorption. The second term is lost due to scattering. The third term is a gain term due to scattering. The second term is a gain term due to backscattering, and the last term is a gain term due to scattering for light that came from the other direction. Well, why all these manipulations? Well, as you can see, the second and the third term are the same apart from the sign. So these two cancel. So we can simplify this as the equation that is now on the slide. Change influx in the positive direction is given by the flux times the coefficients as a loss term plus it's not so strict loss and gains anymore now, and a term that depends on the flux that was originally going in the negative direction. The interesting before I go on, the interesting thing now is that this is only now a function of the absorption coefficient and the backscatter coefficient. So the scattering coefficient itself we have basically got rid of. So it is only a function of the absorption coefficient and the backscatter coefficient. So only about reversing directions. Now, of course, we can do the same exercise for the flux in the negative direction. I'm not going to repeat all the terms again, but the analysis is more or less the same. So we first write out all the gains and loss terms. Then we work, we try to get rid of. Then we take a differential. So we let the volume go to dx to a very small value, so that the left-hand side becomes a differential. For the loss terms and the gain terms, we try to factor out the phase function and write that in terms of the backscatter coefficient, regroup, and we get the same kind of similarly looking equation for the change in the flux in the negative x direction, and again as a function of mu a and mu b only, and a term that is dependent on the original flux in the negative direction, and a term that is dependent on the flux in the positive direction in that volume. Okay. A lot of manipulations, not something, like I said, that I'm going to ask you about, but just to illustrate how these things can be approached. What is important is that it is a function of absorption and backscattering only in 1D. So the scattering coefficient itself is not important. It is the product of the scattering coefficient and the backscattering probability that determines what goes on. So these were the two equations. We can, of course, we would like to try to find a solution. So these are two coupled differential equations because well, because of the cross terms in there, they are coupled. And if we would if we want to solve that, we need boundary conditions. Luckily, we have a few. We know that at the entrance of our long cylinder, so at let's say x is truly 1, so on the left-hand side, then the flux in the positive direction is equal to the incident intensity. So F plus of x at x is 0 is equal to the input intensity. Also, we know that there is no light. There was only light coming in from the left-hand side. There's no light coming in from the right-hand side. So at the other end of the cylinder, at x is d, the flux in the negative direction is 0. There is no light coming in there. So we can use these boundary conditions. Now, usually, what you do is to find a solution of these type of coupled differential equations is to try some functions of exponential forms. So let's say if the form a times exponential c of x and b is exponential minus d of x, something like that. So, and then using these boundary conditions, we can try to find expressions for a, b, c, and d, and then if that works, then we have solved the differential equation. Okay, we can do that, and we have the fluxes. That is interesting, but even rather, we would have some expressions for the things that we can actually measure. So the measurable quantities in this case are the reflectance, which is the light that escapes from the cylinder on the side where we illuminated it. So that means that we can calculate the flux in the negative z direction. So it's escaping from the cylinder at the x is 0 boundary. So that would be a number in watts per square meters. If we divide that by the incident intensity, also watts per square meter, then we get the dimensionless reflectance. So just a fraction of the incident power that is reflected back. Same thing we can do on the other end of the cylinder. So at x is d, we can measure the transmittance. So we can calculate the flux in the positive z direction at x is d. That is the light that escaped from the cylinder. And if we normalize that as well on the incident intensity, we get a percentage of light that is transmitted from the cylinder. And of course, if the absorption coefficient is 0, so if light can only bounce back and forth, then R plus D should be 1. But if the absorption coefficient is non-zero, then some light, of course, is absorbed in the cylinder. So then it's a little bit more complicated. Okay, let's take a look at the solution. So I've sketched the approach, how we can do that in the previous slide. If I define help variable, so the variable m is mu a plus mu b divided by mu b, and the variable b is the square root of m squared minus 1. Seems a little bit arbitrary at this point, but if we define these help variables, then we can find the solutions. And here they are. The flux in the positive direction as a complicated expression, and the flux in the negative direction at a certain point x also as a complicated expression. So let's take a closer look at these solutions. So let's take f plus, for example. In terms of the help variables, we see that we have as an argument in these expressions, we have the product of b times mu b. That is a variable. That is something that depends on the optical properties. So the optical properties go there. D and x are geometrical variables. So they are only there. What you can also see is that the denominator of this expression is a constant because there is no x in there. So that is just a scaling. That is just a constant. Further, sine h of x and cosine h of x are the hyperbolic functions. I've quickly written the definitions, the definitions of those in there. So basically, they are these exponential functions from which I said we're going to try a solution in this form. And indeed, if you do that, you get as it turns out, you get an answer which contains these exponential functions. Basically the constant of the coefficient of these exponentials is this b times mu b. That was given in blue there. So if we work that out a little further, we see that we can rearrange that so we can fill in for m, and we can then in turn fill in for the absorption coefficient and the backscatter coefficient. which allows us to define a new coefficient, the effective decay constant, or the effective attenuation coefficient, given by this expression. So this b times mu b1 is the effective attenuation coefficient. It's the square root of mu a times mu a plus 2 times mu b, or if you rearrange that in terms of the scattering anisotropy, you get this the expression on the right hand side. So basically, the main point here is, again, it depends on it only depends on the optical properties. It depends on the absorption coefficient, clearly, and it depends on the product of mu s and, in this case, 1 minus g. So the exact values of mu s and g are not what go into these formulas. It is the product of these two that goes into that. All right. So we can continue that. We can look at the total flux. So that would mean adding the fluxes in the positive and in the negative direction would be the total power flowing through that area in all directions, the fluence rate. The physical importance, as we said a couple of slides ago, is that if you multiply the fluence rate with the local absorption cross section, you get the local absorbed power, and if you multiply it with the fluence rate with the absorption coefficient, you get the absorbed power density, how many watts per cubic meter you are basically dumping in the tissue. Yeah. Okay. So the next goal is to take these these expressions for the fluxes in the positive and negative direction, and then transform them into coupled equations for fluence into equation for fluence rate, one equation for the fluence rate, because essentially that is what we want to measure. So again, I'm going to this derivation is just to illustrate how it goes, and that you can show that you can actually do it. And along the way, a few important conclusions can be drawn. So this is the set of equations that we have to work with. And if you want to transform this into a differential equation for the fluence rate, we know that the fluence rate is the sum of the fluxes, and that means that the derivative of the fluence rate is the sum of the derivative of the fluxes. That is the set of equations on the right there. So we can take all the terms and we can combine them, and then we get an expression as follows. So on the left hand side is the spatial derivative of the fluence rate, and on the most right hand side is an expression in terms of optical properties, mu a, mu b, and in terms of the net flux, the difference between F plus and F minus. So we can express, so basically what we have now is a single differential equation that expresses the fluence rate, the sum of the fluxes, in terms of the net flux, the difference of the fluxes. So again, combining this is combining these equations, we can simplify it a little bit, and this is the resulting remaining expression. So fluence rate is the sum of the fluxes, and capital F without the subscript there is the net flux, the difference of the fluxes. Okay, let's take this one step further. We can calculate the second derivative of the fluence rate. So differentiate again. The optical constants are just that, constants on the right-hand side, so they remain the same. And taking the derivative on the left-hand side also on the right-hand side means that we take the derivative of the net flux. So we can tackle that as well. We know that the net flux is the difference between the fluxes. We had expressions for these fluxes. So the differential of the net flux is the difference of the differentials of the positive and negative fluxes. And if we write that down, we see now that this becomes that this is dependent on the sum of the fluxes, so on the fluence rate. So where we first had an expression where the fluence rate dependent on the net flux only, we now have an expression, a differential equation for the net flux that depends on the fluence rate only. So combining that, and this is actually the second equation is quite important. It says that the change in net flux is proportional to mu a times the fluence rate, and basically this was the amount of power that was dumped in the volume of tissue. It's also exactly valid in 3 dimensions. So changes in net flux in 3 dimension is given by an absorption loss. And basically this is just a conservation of energy, a statement of a conservation of energy. So if the net flux decreases over a volume, um, scattering does nothing but change the direction. So if there is a loss of energy, then it has to come from absorption of photons in this volume, because there are no other loss mechanisms in this case. So it is so that is why only the absorption coefficient appears here. Okay, so we can now take this expression for the second order derivative of the fluence rate and combine the results above. We now have a single uncoupled differential equation for the fluence rate only. So the second derivative of the fluence rate with respect to x is given by a constant that depends on the optical properties times the fluence rate itself. And you remember that a couple of slides back for this constant in front of on the right hand side we had defined an effective attenuation coefficient mu f EF. So we can compact the expression a little bit further. A simple, straightforward second order derivative of a differential equation with a constant mu effective like this. A solution for such an equation is basically textbook. So as given here, a sum of 2 exponentials, one with the plus, one with the minus, but with mu effective as a decay constant. We can apply the same boundary conditions for at x is 0 and x is d to solve for the constants c1 and c2. And then the result is again such an expression in terms of these hyperbolic functions, again with a denominator, sorry, that is constant, and in the numerator we have something that depends on position. And just as a fresh up, this is what the parameters appearing in this formula are. All right. So what did all this manipulation and all this derivation gives us? Well, we have analytical expressions for the forward and the backward fluxes at some location x inside our 1D volume, which means we can later on proceed to make a graph of that and see how it behaves. We have an expression for the net flux given here, and we have an expression for the fluence rate, the sum of the fluxes, given here. So let's look at some examples. Let's indeed make this plot. This is a slab of or cylinder of finite length, finite thickness d, 5 millimeter. It is illuminated with an intensity of 1 watt per square millimeter. We have a moderate absorption coefficient, and we have a 10 times stronger scattering coefficient in there. On the horizontal axis, you see the depth inside this tissue, inside this cylinder, ranging from 0 to 5 millimeters. And then on the horizontal or on vertical axis are the magnitudes of the different curves that are shown there. So first, the flux in the positive direction. Let's the green curve F plus. So let's see if the boundary condition holds. So at the depth is 0. We said the boundary condition was that F, the flux there in the positive direction, has to be equal to the incident intensity. And indeed, this is the case. It's 1. On the other hand, we had that for the other boundary, that the flux in the negative direction going into the cylinder at x is 5 in this case had to be 0, and that is also shown in the red curve. That works as well. Well, subtracting these 2 curves gives us the net flux. That would be the black curve, and adding these 2 would be the fluence rate, the blue curve, and the blue curve is the important one in this case. Is there anything that strikes you about the curve of the fluence rate? I mean, especially at a shallow depth. So at a depth of, let's say, 0.1 or something like that. Is there anything that strikes you about it if you compare it to the value of the input intensity? Yeah. So yeah, it's steep. That's true. But that is so the steepness is. So let's tackle the steepness first. That is determined by this effective attenuation coefficient, which was this compounded expression of mu a and mu s. So if I would have chosen different values there, then the steepness would change. That is one thing. Vlad, you say it is much bigger than the input intensity, right? Yeah, Chan as well. Uh, yeah, it's bigger than the input intensity. So that means that I put in 1 watt per square millimeter, but just below the surface, I have 1.6 watts per square millimeter. Um, this is the case because you remember the fluence rate was the sum of the fluxes in the positive and in the negative direction. So what you have just below the surface is you have a flux in the positive direction, which is still almost equal to the input intensity. But because light that has already been sent into the tissue, part of it is scattered back and will constitute a flux in the negative direction, uh, also just below the boundary. So that power is also flowing through the volume just below the surface. So you have two contributions there: one from the input intensity directly below the surface, and one that is due to the backscattered light, the backscattered flux, or the flux in the negative direction. If you do a 3D calculation, then you'll find that this effect is even stronger. Yes, so that is due to backscattering indeed. This so when is this important? Well, for example, if you want to do uh, if you want to do okay, let me give you an example. People have been doing ablation of tissue, so trying to burn tissue away. For example, in the bladder. Uh, what basically happens is that you put an optical fiber uh, in, into the bladder. There's a small uh, uh, light source or a diffusing light on the tip of the fiber that shines light into the bladder. So you get a few effects. So first of all, uh, consider this bladder. So it's filled with water. So it's kind of like a balloon filled with water. There's this light source in the middle that shines light in all directions. So what you get is first that some of the light is reflected directly from the bladder wall, so that bounces around a little bit. And the net result of that is that you get a nice nice uniform illumination all across the bladder. Uh, so you can just put a somewhat imperfect light source in there, and then but the result uh, in the end, because of all these reflections going back and forth, is that you get a nice homogeneous illumination. Uh, so people calculated that. So what they basically then knew is the incident intensity. They knew E on the bladder wall. But then it turned out if they wanted to ablate, they made much more damage than they expected. So they did the calculation. They calculated how what the power of the laser needed to be in order to reach the right intensity to do the right amount of damage. But it turned out that they did much more damage, and that was due to this effect. So what they did not consider first, so this is years ago, of course, what they did not consider is that there was also light, so not only these reflections inside the bladder of the walls, but that there's also light that has entered the bladder wall, but which is reflected back. So the fluence rate just below the surface of the bladder wall was much higher than the incident intensity, just like in this graph. Uh, and fluence rate multiplied with the absorption coefficient gives you the amount of power that you actually leave there in order to do damage. So Yeah, so basically what they had to do is scale back their laser power in order to do the right amount of damage. We can actually estimate how much we have to do that, because remember the definition of reflectivity. R is equals the flux in the outgoing direction, so in the opposite to the incoming direction. If we normalize that on the incident intensity, we have an expression for reflectivity. Now, if we rearrange that, that means that F minus at the surface, at 0, is equal to the reflectivity times the incident intensity. So now we can write for the fluence rate at the surface or just below the surface is the sum of both fluxes. For the incident intent for the flux in the positive direction, that was equal to the incident intensity. For the flux in the opposite direction, we just found that it is equal to I times R. So combining these two, we find that the flux just below the surface is equal to the incident intensity plus this factor that describes the buildup is 1 plus R. And R is the reflectivity of the tissue. So what you can do, and this is when it all comes together, you can do a measurement of reflectivity. If you can do some kind of measurement with another technique or another fiber, or if you can estimate the reflectivity, you can exactly calculate this build-up factor. So you can exactly calculate what the fluence rate is going to be just below the surface. Let's take an other example. This is a very thick slab. So now it's 100 millimeters thick. There is no absorption, so the absorption coefficient is 0. But otherwise, the numbers are the same as the previous example. So we have 1 watt per millimeter incident intensity and a scattering coefficient of 1 per millimeter. So the same thing holds for the flux in the positive direction, that the horizontal axis is on a logarithmic scale now. So the most left-hand side would be just below the surface. The flux in the positive direction at the surface is equal to the incident intensity, I0. Also, the flux in the negative direction at the other end of the sample is equal to 0. But since there is no absorption, there is no losses. Light can only either be transmitted or reflected, and that is expressed here as basically the flux in the positive and the negative directions being equal at all locations. The difference of the two, the net flux being 0 everywhere. So net, there is as much power flowing in one direction as into the other direction. And now we see the limiting or the extreme buildup that we can get for the fluence rate. So if the flux in the positive direction and the flux in the negative direction are the same, then the sum is simply twice, for example, the flux in the positive direction, and just below the surface, that is going to be 2 times the incident intensity. So that is the maximum fluence rate that you can achieve just below the surface. Okay, another example. Let's take now a very, very thick piece of tissue, so 10 millimeters in this case, not as thick as in the previous example, but still pretty thick. 1 watt per square millimeter incident intensity again, a mu A of, so adding a little bit of absorption again of 0.1 per millimeter, scattering coefficient the same. And now let's take a look at the reflectivity. So again, the reflectivity was the escaping flux in the minus x direction. If you divide it by the incident intensity, we get the reflectivity. So what you see here is that that if you look at if you would take a tissue thickness, I'm sorry, the tissue is not 10 millimeters thick. The tissue thickness is varied on the horizontal axis. My apologies, I didn't explain it clearly enough. So if you have a very thin piece of tissue, then the reflectance is going to be very small. So for a 1 millimeter thick piece of tissue, for example, the reflectivity is about 0.4. But you can also see that if you make the tissue thicker and thicker and thicker and thicker, then the reflectivity approaches some asymptotic value. Well, if you take the equations that we had before, you can let d go to infinity, and then we'll find that this asymptotic reflectivity is given by m minus b, and m and b both were functions of the optical properties mu a and mu b. So there's going to be some saturation in the reflectance, which basically tells us that in the end, the light, if the tissue becomes thick enough, then the light can either be absorbed or reflected, because if the tissue is infinitely thick, there is no transmission. So that is what this example tells us. So for an and that's actually quite a useful model medium if we want to do some calculations at times. So make the tissue really semi-infinitely thick, so d goes to infinity. Then the reflectance, for the reflectance and transmissions, we have that the reflectance becomes this limiting value, m minus b. Below the dotted line, you can see how m and b depend on optical properties, and the transmission is going to be 0. Also, the expressions for the fluxes simplify in this case. For d goes to infinity, they become simple exponentials. So the flux in the positive direction is a simple single exponential I times exponential minus x times the effective attenuation coefficient. The flux in the other direction, in the negative direction, is also a simple exponential, and the net flux, and also a simple exponential. So basically, these look an awful lot like Lambert-Beer's law. The only difference is now that because this light can go back and forth, the net decay of the net decay of light is a little bit slower than if it were only absorption or only scattering. But in essence, it is just again a manifestation of Beer's law. For the fluence rate, we have the important property. We have this expression, so it's equal to the incident intensity times this boost factor, 1 plus r, and then again a simple single exponential. All right, I think we should stop here. The original title of this class was Transport and Diffusion, but we only did transport. So I will record the diffusion slides. I will put them on Canvas. I will try to do that tonight, and in that case, they are your homework. Looking at these. And there's another issue we need to discuss. I've put the first assignment on Canvas. Don't rush to it because I still have to make it visible, but it will be available in a couple of minutes. It's on Monte Carlo. The description is in the document. I hope it is self-explanatory. If it is not, do not hesitate to contact me in any way, because I want you to succeed with this assignment. That is the goal. As for the rules of engagement, this assignment counts as 25% of your grade, of your final grade, and there will be 3 of these assignments, so up to 75% of your grade will be given by these assignments. For these 3 assignments goes that you can make them yourself, then you will get your own grade, or you can make them in a group of maximum 3, and then you will get then each of you will in the group will get the same grade, of course. You can do that, but I do want you to change groups between assignments, so you can work that out yourself, but you must change between assignments because otherwise people get the same grades. And then after that, there is an oral examination that will be about 20 minutes, half an hour. That also counts for 25%, but it is must pass. So you must have a pass for the oral exam. So you cannot. Yeah, basically that's it. The assignment folder is empty. Is that correct? For a second, I will do the click. If you can you try again? Should be there now. It is the assignment folder on top of the. Okay, Excellent. Okay. Any questions about anything?
Is there a deadline for this first assignment?
Good point. Good point. Yes, 1 week. So let's say before the class of next Monday.
Okay.
And I would appreciate it if you would if you actually decide to do it in a group. I would appreciate it if you would let me know which groups that way I can keep a little bit track of that. I will send an announcement detailing this as well. All right. If there are no further questions, then this is it for today. I will record the part about diffusion, and I'll post that as well. And that will be homework. All right. Have a good evening.
Bye.
Thanks, you too.